We're now going to revisit the ideas of velocity and acceleration in our nonlinear motion and see if we can tie some of the recently discussed ideas together, right? Thinking about things like our unit tangent vector, unit normal vector, and so forth. How are those things related to velocity and acceleration? And let's start with velocity. Let's see what we know, right? So you have your position function. And we know that the velocity is equal to the derivative of position, right? Well, the unit tangent vector, so our unit tangent vector is equal to, remember how we found this? We would find the derivative of the curve and then normalize the derivative. So let me write this. So the magnitude of r prime of t. But r prime of t is just the velocity, right? So I can write that the unit tangent vector is simply the velocity vector divided by the magnitude of velocity. But what's the magnitude of velocity? It's speed. And we actually have another way of writing speed. Based on what we did with the arc length, or speed is ds dt. So that means, oh, I crossed the wrong letter. So what that means is I can express my velocity function as, so therefore, my velocity is equal to, just take this denominator and multiply my unit tangent vector. So it's my speed times my unit tangent vector, right? And this makes sense because we know that the velocity, which is our first derivative, the first derivative is going to be tangent to the curve. This is tangent to the curve, but it has magnitude 1. So this is a unit vector in the direction of velocity. And we're multiplying that unit vector by the speed. And that's how we get the velocity vector. So essentially what we have here, we've broken velocity into its two, I guess you could say, components. This one is a scalar component. This is the vector component. So this is the magnitude of velocity, right? And then the t is a unit vector parallel to velocity, or in the direction of velocity. So unit vector in the direction of v, right? So multiplying those two, you'll get the velocity vector, right? And what we would like to do now is something similar for acceleration. But acceleration is, it's a little bit more involved, so let's see if we can work through it. Now, suppose the magnitude of the velocity, which is the speed, suppose that is equal to a constant, right? Some constant k. Well, we've used this fact several times. If the magnitude of a vector function is a constant, then the vector itself and its derivative must be orthogonal, right? This is something we proved previously. If a vector function has constant magnitude, then that vector function and its derivative, assuming it's differentiable, right, are orthogonal. Well, what does that mean? Well, think about it. V prime is the acceleration. So this means, so therefore, v of t and a of t are orthogonal. So that means if the speed of my, let's say my object, or the speed of the curve, right, is constant, then it means the velocity vector and the acceleration vector are going to be at 90 degrees. So it's they would look like this. You would have your v, and then you would have your a. So you would, in this case, the A would simply be acting in a direction that is normal to or orthogonal to V. But think about it. We have our unit tangent vector, which would be this. So that's T. And then we have a vector that's orthogonal to it, and that's our N. Right? So basically, whenever velocity and acceleration are orthogonal, right, and that occurs when the speed is constant, you will have velocity be a scalar multiple of t, and acceleration will be a scalar multiple of n, right? So in this case, I'll just write it now. That scalar, I'm just gonna, for now, I'm just gonna say some scalar. We're not gonna write it down explicitly just yet, but this implies now that our v of t in this instance is some scalar times the unit tangent vector, and the acceleration vector is some other constant times the principal unit normal vector, right? But this is true. Well, this one is always true. This one is true whenever V and A are orthogonal. But what if they're not orthogonal? What if they form some other angle? So if the speed is not a constant, so if your speed depends on your time, so it's time dependent, then we have the following. So I'm going to start with a picture and then derive some results. So I'm just going to focus on A now. That's what we're trying to figure out. So you'll have your curve, and then at some point, I'm not even going to draw the V because I don't want it to get too messy, but you'll have your velocity there, which will be a product of your speed times the unit tangent vector. And then you'll have your acceleration, which won't be at 90 degrees. So you'll have your acceleration vector somewhere like that, right? So I'm just going to call this, I'm going to write it here, A. And then this would simply be the magnitude of A. That's the just the magnitude of that vector. And what we would like to be able to do now is express this vector, right? Since since A in this case does not is not a multiple of t, and it's not a multiple of n, it's somewhere in between, so we should be able to express it as the sum of two vectors, one that is parallel to t and one that is parallel to n. In other words, take that one vector, and let me draw my t. So here's the unit tangent vector, and here's the principal unit vector. So I gotta make it 90 degrees. So probably about here. Right? So what I would like to do is to express this vector A as the sum of multiples of t, t and n, right? So basically, if I were to complete my parallelogram. So if I did it like that, and then like this, and then this is also my red vector, and then this is my green vector, right? So let's say that this length here is some constant times t, because here's my unit tangent vector t. So this length is a constant times t, right? In fact, or I should say that vector is a constant times t, and then this vector is a constant, another constant. So let me write it over here. This one is a constant times n, right? So by our parallelogram, we can see that A is equal to something times t plus something times n, right? So therefore, A is equal to some constant times the unit tangent vector plus some other constant times the principal unit normal vector. And the question is, what are these two scalars? Well, so what do we have right here? We have a right triangle. So let me just draw the triangle. Again, not to make it very messy. So here's the triangle. Essentially. And let me just draw the magnitudes now. So let's say that this is our angle. And this is theta, this is the right angle. This side is just the magnitude of A. This vector, right, this would be its magnitude. It would be C1. And then this vector here, this green vector, would have magnitude C2. So what do we have? Well, we can use a couple trig identities to get a relationship between the magnitude of acceleration and, these two constants, C1 and C2. So if I start with C1, I could say that the cosine of theta is equal to C1 over the magnitude of A, right? And same thing, I could say that the sine of theta would be C2 over the magnitude of A. Let me put my harpoon there, right? So this tells me that C1 is equal to the cosine of theta times the magnitude of acceleration, and this tells me that C2 is the sine of theta times the magnitude of acceleration. Okay, so then what can we do with these equations? Well, let's, if I take this equation, let me rewrite it. So I have that C1 is equal to the cosine of theta times the magnitude of acceleration. Let's say I multiply and divide by the speed, right? So in other words, I'm going to take this, I'm going to multiply by the speed, which is the magnitude of velocity, and then divide by the speed. So just kind of balance this out. Well, why do I do that? Because if I look closely at this, going all the way back to our dot product, this is the definition of the dot product of A and V, acceleration and velocity. So this tells me that the numerator here of C1 is V dot A, and the denominator is the speed, which I'll just keep on writing as the magnitude of V. So this gives me a way of figuring out what the scalar is that we'll have to multiply our unit tangent vector to get that component of acceleration, and then to get the component of the parallel to the normal vector. Let's see what we can do with the other equation. So what does this mean? So C2, well, if I do the same trick, and I take this equation that I have for C2, which is the sine of theta times the magnitude of acceleration, if I multiply and divide again by the magnitude of V, like this, then what do we get in the numerator? This is now the magnitude of the cross product of A and V. So you might remember, again, this was another property that we came up with the cross product. So this is the magnitude of the cross product of V and A, and then again, this is all over V, right? So these two scalars, so what this means, so this implies that my acceleration vector can be written as this constant, so V dot A over the magnitude of V times the unit tangent vector, plus this scalar, the magnitude of V cross A over the magnitude of V times the principal unit normal vector. And we have some special names for this. This coefficient of t is called the tangential scalar component. So, and it's usually written like this, little a t times our t, and then this scalar that's multiplying the n, this is the scalar normal component of acceleration. So then we denote it like this. So it's a scalar and it's normal, and then times our principal unit normal vector. So here we can express the acceleration as a vector that is parallel to the unit tangent vector plus another vector that's parallel to the principal unit normal vector. So let me write down those terms. So a sub t, that is defined as the tangential scalar component of acceleration. A sub n, that's the normal scalar component of acceleration. When you take your scalar tangential, so at times t, this is defined as the tangential vector component of acceleration. And then when you have your a sub n times n, let me put the harpoon on those, that's the normal vector component of acceleration, right? So it allows us to break up acceleration in terms of t and n. All right, so let's do an example to just kind of illustrate this. So let's write example. So let r of t be equal to ti plus t squared j plus t cubed k, right? And we're going to go through and find several expressions. So first, let's find a sub t. So a sub t, the tangential scalar component, that is v dot a over the magnitude of v, right? Well, it means we have to find the first derivative, the second derivative, and then divide by the magnitude of the first derivative. So let's write down what v and a are. So our velocity vector is I plus 2tj plus 3t squared k. And then a, now since the coefficient of I is a constant, then its derivative is going to be 0. So I'm going to be left with 2j plus 6tk, right? So let's find the dot product of these two. So v dot a, well, this will be 1 times 0, so that's 0, plus 2t times 2, so that's 4t, plus 3t squared times 6t, that will be 18t cubed, so 18t cubed, right? So that's going to be my numerator, and then the denominator is going to be the magnitude of v. So I have to take the magnitude of this vector, or essentially my speed vector, right? So in this case, it's going to be 1 squared plus 2t squared plus 3t squared squared, and then I take the square root of all of that, right? So where do we go? So the numerator is 18t cubed, the denominator, plus 4t, and then the denominator is, and let's write what's under the square root in decreasing powers of t. So this is 9t to the 4th, and then we have plus 4t squared, and then plus 1. And there we go. So this is our scalar tangential component of acceleration as a function of t. So for different values of t, we could evaluate this. Let's do the same and compute a sub n. The normal, so this is the scalar normal component of acceleration. So this is the magnitude of v cross a over the magnitude of v. So here we have to do our cross product and then find the magnitude. So let's do our cross product off to the side here. So we have our vectors. So v cross a. So let's set up our 3 by 3 determinant. We'll put the components 1, 2t, and 3t squared, and then 0, 2, and 6t, right? So let's see what happens. Now, if we block out so here I'm not going to write down the actual 2 by 2 determinants. We'll write down the expression for each of them. So when I block out the first column and the first row, I'm left with the 2 by 2. So it's 2t times 6t, so that's 12t squared minus, and then 3t squared times 2, so that's 6t squared. And then that's times I. And then I'm going to have minus the quantity. Now block out the middle column and the first row. and you'll be left with the 2 by 2, 1 times 6t, so that's 6t, and then minus 0, because you have 3t squared times 0, so minus 0, and then that's times j, and then plus, block out the third column, first row, then you have 2 minus 0 times k. So this is what we're left with for the components of the cross product. So we have, so what's this? 6t squared, right? I. And then we have minus 6t j, and then plus 2k, right? Now we need the magnitude of this. So the magnitude of this vector, square, so 6t squared plus negative 6t squared plus 2 squared, and then all under the square root. And what do we have there? We have 36t to the fourth plus 36t squared plus 4. And then this is all under the square root. Now, we can actually factor out of 4 out of all of these. So if I take out a root 4, then I'm left with root 9t to the fourth plus 9t squared plus 1. So it's 2 times root 9t to the fourth plus 9t squared plus 1. So therefore, we can then write down, so if I take the magnitude that I just computed, which is the 2 root 9t to the fourth plus 9t squared plus 1, and then divide that by the magnitude of v. So the magnitude of v, which is the square root of 9t to the fourth plus 4t squared plus 1, that will give me the scalar normal component of acceleration at time t. Right? And then if we wanted to, we could go ahead and evaluate these to get these components at specific values of time. But I think that that's good for now. Just wanted to illustrate how you would use these formulas to come up with these two components or scalar components of acceleration. And these are quantities that you will utilize quite a bit when you study concepts in dynamics. You use this a lot more, and it's actually also related to the curvature. So there are lots of ideas that come together, and here we're just introducing the concepts and showing you some methods of calculation. So hopefully you get to maybe use some of these ideas in your other courses of study. Well, good luck with those, and I'll see you in the next video.